Okay, so we talked about the quadratic parent function. We did on the very first day. We didn't talk about it a whole bunch, but quadratic parent function was mentioned. That is the equation. It is the most basic function that we have. When it comes to the table, does anyone remember what the vertex was? It's the origin, it's 0, 0. We always want to put the vertex in the center of our tables. And then 1, 2, 3, -1, -2, -3. It's y equals x squared. That means you're squaring the x values to get your y values. So what's 1 squared? 1. Then that's also 1. Remember, they mirror each other. What's 2 squared? And that means it's equal. And then what's 3 squared? Okay. We're going to start quadratic transformations today. The quadratic transformations, we're going to do all function notation today. Good news for you. We have already done function notation transformations. We did it for linear graphs. It's the exact same look, but now it's just for a quadratic graph. But it looks exactly the same. Like we still have our horizontal compressions or stretches. We have our vertical stretches and compressions. Horizontal shifting left and right, vertical shifting up and down. All of that is still the same. So it's all going to still look the same. It's just applying to these quadratic parent functions. So we need to go through, because on all 4 of our graphs that we're about to do, all 4 graphs are going to have transformations from the parent function. So we need to go through and graph the parent function on all of them first. Those ordered pairs, 0, 0, 1, 1, 2, 4, and then 3, 9. And then the exact same thing on the other side. So I'm going to give you a few minutes. You're drawing that parent function on the other 3 graphs. So the last one on the front and then the 2 on the back of the page. Go. Okay, so the function notation is still the same. If something is outside of f of x, is that a horizontal or a vertical change? Vertical. It is still the same thing. We are still looking at vertical stretches, vertical compressions, and vertical reflections. And guess what? It's still the same as linear. If it's greater than 1, outside the parentheses being multiplied, that's giving you a vertical stretch. What does it look like when I'm going to stretch something vertically? So think about the parabola. Think about my rubber band. If I want to stretch that rubber band vertically,
It's going to become tighter.
it's going to become slimmer. It's going to get skinnier. Narrow, whatever kind of word you want to use to describe it. If we're going to vertically compress something, so vertically compress, so pushing it down, what's happening to that rubber band? It's getting wider. And then a vertical reflection, it's going to flip. So if it was opening up, it'll open down. If it was opening down, it'll open up. So it just flips it. Okay. Did any of those describe some sort of movement other than changing the shape, like wide, skinny, or reflecting? So if we aren't having a change to like a shift anywhere, that means our vertex is staying in the same spot. So we're going to look at this first example. When it's outside the f of x part, that means we're multiplying this entire equation by whatever that number is. So this is really 2x squared. Which now we could either figure it out like the long way. We can figure it out. We could put in the different numbers for x and figure out our y values. Or what is a little bit easier to we know the vertex. The vertex isn't changing. Use your calculator. Type this 2x squared in your calculator. I told y'all, calculator's best friend when it comes to, go to the graph section, put that 2x squared in your calculator. So we want to try and graph the best that we can. As of now, we can graph the origin, or the vertex at 0, 0. We can graph 1, 2, negative 1, 2. We can graph 2, 8, and negative 2, 8. After that goes off our grid. That's okay. is that showing that it just got skinnier? Yes. Okay. Let's look at the next one. The next one, if it is outside the parentheses, that means we are multiplying this entire thing of x squared by 1/4. So 1/4 times x squared. Vertex isn't changing because we aren't doing any type of shift. So it's still at 0, 0. Now type that into your calculator, get the table. Before we put our things into the table, did y'all notice what kind of numbers do we now have for some of those y values? Decimals. We can put those in our table if we want, but it's usually easier to graph the whole numbers. So I changed up my table. I didn't give y'all specific x values for a reason. That way we can kind of alter the table to fit with our numbers that's best. So like 2, 1, and then 4, 4, and then 6, 9. And then it would go the other way of -2, 1, -4, 4, -6. Now, do you have to do that? No. It's just makes graphing. I think it makes graphing a little bit easier to use those whole numbers. It makes it look a little bit more accurate. Okay. And then on the last one. The last one is a vertical reflection because there's a negative on the outside. Is there any number that's going with it? Just a -1. So that means we're just flipping this to make it -x squared. Guess what's going to happen? Can anyone make a pretty logical guess of what our points are going to be without using your calculator?
Are they going to be going down?
We're just flipping this. So it's still going to be 1, 4, and 9, and 1, 4, and 9, but we reflected it, meaning you need the opposite. Oops, there's no -0. My bad. Now you could have put it in your calculator if you wanted to, just -x squared. It will give you all these same points. Okay. So let's take a look down below. Now it's adding something or subtracting something outside the parentheses. So what kind of change is that going to make? Outside the parentheses. Always need what? Vertical. So we're going to look at our vertical shifting up or shifting down. Now, vertical shifts, normal. If it has plus something, if it has a plus something, it's going to greater than 1. It's going to be going up. Less than 1 is going down. Or 0. Sorry.
I thought like it was supposed to be.
I was ignoring. Okay. So on that first example, what's going to happen to it? It's going to go up 3. Did it have any multiplication to it?
No.
That means the width of it is not changing. It is staying this exact same shape, just shifting up. Correct. So all we're doing is shifting it up. So you have 2 options. Option 1, you can put that in your calculator. Your calculator will help you get your table. Option 2, the vertex is just shifting up 3, and all other points just go up 3. So this point is going to go up 1, 2, 3. This point is going to go up 1, 2, 3. And then that last one doesn't fit in the elastics. So it's not changing the width of it. It's not making it compress or stretch. It's just a shift. What's going to happen on the second one? Right, it has plus a negative, which really means minus 2. So it's x squared minus 2, meaning down 2. Origin is changing, or that vertex is changing. It's now at 0, negative 2. All other points are staying like in that same type of position, just shifted down 2. So this one's going to go down 2, 1, 2, down 2, down 2, and down 2, down 2. Looking at just, if I'm giving you that function notation, the things that happen to it. On that first one, what's happening? Down 4. What about the next one? Up 2 4/10. What about the next one?
That's a
Vertical compression. And something else.
and a reflection.
And a vertical reflection.
Oh, it's negative.
Yeah, that's a negative sign. I know. The fraction is kind of hard to see it. What about the last one?
Vertical.
Vertical stretch. And up. Very good. Okay. Flip to the next part. Next part's going to be our horizontal part. Well, we have horizontal changes. Where are the numbers located for horizontal changes when it comes to function notation? Inside the parentheses. All right. So, remember with horizontal, if it is a horizontal compression, now look at my rubber band. If I'm compressing something horizontally, what is it going to start looking like? It's looking skinnier, or it's looking narrow. It looks similar to a vertical stretch, but it is a horizontal compression. Same thing with a horizontal stretch. Stretching something horizontally makes it wider. So remember, it looks similar to a vertical compression. The thing to always remember, though, if that number multiplying is bigger than 1, it's always going to look skinnier. It's always going to look more narrow. If it is less than 1, it is always going to look wider. You just have to pay attention to where is the number, inside or outside, because that's going to control whether it's the vertical change or the horizontal change. All right? So here's our parent function. Now our changes are inside the parentheses. That means whatever this parenthesis is plugs in for x. So when it comes to our equation, it's 4x, because that was our parentheses, and the squared is outside of it. And that is what you can put into your calculator. So go ahead and put that in your calculator. So when it comes to graphing this one, there's really only one thing that we can graph. Vertex. The next ones would be like way up here. I don't know. Just try the best you can.
That looks good.
Okay. So then, looking at the next one. It is inside the parentheses, and it's a fraction less than 1 inside the parentheses. That means, what is it going to look like? It's going to look wider. When it comes to putting it in your calculator or plugging it into the equation, if it's ever something inside the parentheses, and that is no longer just x, that means you are replacing the x part in your equation with whatever was in that parentheses. So this is really 3/5 x, then we square it. Make sure you're always using parentheses when you're putting it in your calculator. So go ahead and do that, and let's talk about the table. Instead of trying to make a graph, so if we just went in that same order of using like 1, 2, and 3, all those decimals are really small. You're not going to get a super accurate looking graph if you use decimals that are really small. So if you can, scroll down to some of those whole numbers. You should get to the first whole number at 5/9 or -5/9. And then 10 and 15.
10 and 36.
So 10 and 36, and then 15 and 81. So then 36 and 81. You don't have to do this. It's just kind of helpful. I like graphing whole number points when possible. If we had this problem, everything was a decimal, okay, whatever, we'll get over it and do just the decimals. But if possible, I always like to go towards those whole numbers.
Alright.
We were able to get 3 points on there. 3 points is not bad. That's minimum. 5's a little bit better, but oh well. Okay. Now for the last one. Horizontal shifting left and right. Who remembers the trick about horizontal shifts?
It's opposite.
It's the opposite. So on this first one, f of x minus 9, this is really going to go right 9. What about the second one? It's really a plus sign, meaning we're going left 9. Now when it comes to putting it in your calculator, this is our parent function. Since inside the parentheses changed, that means that is replacing our x value before we square it. So this is really x minus 9 squared. Am I changing anything, like stretching or compressing it? Okay, so you have two options. Option 1, type what I just wrote in your calculator and figure out your table. Option 2, we already know the change that's happening. What's happening to all those points? They're all just moving right 9 spaces. So you could also just count it out and move it over. This moves 9, this moves 9, that moves 9. Move 9. That doesn't fit anymore, but if we wanted to sketch it on there, we could. What's the new vertex? 0 what?
0 on the side. Or 9, 0.
9, 0. And then we always want to put the origin or the vertex in the middle of our graph, our table. So then just go in order for the rest because we have whole numbers. 1, 4, 9, 1, 4, 9. Okay, the second one, 2 options. Option 1, we know that this can just get replaced in our equation for x. So the new equation would be x plus 9 squared. And that can go in our calculator. We can get our table that way. Or option 2, we know the direction that everything's going to move. Which way is it all going to move? Left 9. So we can just shift everything to the left 9 spaces. What's the new vertex for that graph? Negative 9, 0, and then going in order for the rest. Negative 10, negative 11, negative 12. And then negative 8, negative 7. Identifying those changes, just given function notation. What's happening on the first one?
Left 8. Or
Left 8. What about second one?
Horizontal.
Oh, horizontal. It's a fraction less than 1, so it should look wider. So a horizontal stretch.
And then right.
And then right 3. Okay. The next one's being multiplied by a number greater than 1. That means it should start looking more narrow. But what is that called? A horizontal compression. And then right 7. Opposite direction. And then the last one, what's happening to it? Horizontal compression. Okay. The next page is your homework. On this page, it looks like a lot more than it actually is.